Okay, I can see 14 people in the class, and that's not very encouraging for today's class because I want to have a viral discussion with the class. So we are going to spend the first 10 minutes in the chat room. And I want those of you who are already present to cooperate with feedback, with quick feedback, so that we do not waste time because we have work to do today. So I'm going to maybe I can even start the video so that you can see, because I've already recorded what I wanted to discuss on the, I recorded it on the slides. So let me just bring up the slides. Okay, so let me bring up the slides. So slideshow from current slide or from the beginning. Okay, so like I said, I will just go through the first 5 slides and we go to the chat room. It is my desire, homework test and exam, it is my desire to have completed awarding 60 to 70% of your grades prior to the final examination at the end of the term. What that means is that if you are a serious student, you should have already passed even before the final exam. If you are not a serious student, you might have failed so much that the exam cannot help you. So, you know what I mean? Spend a lot of your time practicing and cooperating and collaborating and submitting your assignments and being punctual. Because I desire to award 60 to 70% if it is permissible. Sometimes the university doesn't allow us to give more than 60%, between 40 and 60%, but I want to give up to 70%. Out of that, or in addition to that, 5% of marks will be given for class participation. That means that you're asking me a question in class, you're making a contribution in class, or whatever you do that shows up on our chat room. Actually, when we are going to look at the number of times you appear, where I'm not going to tell you how many number of times is the minimum. If you don't appear at all, you are going to get 0. If you appear too few times, you are going to get maybe 1. If you appear frequently enough, you get 4 or 5. So it is, you are not going to be judged on the quality of your performance. So the person who appears to ask a question is as recognized as the person who appears to answer a question. It's the same thing. All we are talking about is participation in class that shows not only that you are attending, but that you are active. That's all. That's going to be this. That's going to decide 5% of your grade. I shall have completed creating a collaborative environment for sharing my drawings with you before the end of the week. Today, I want everyone in this class to use the chat room to supply me the following information. Now, I will share with you my drawings so that you can go through the steps of my own drawings if you are interested. But I want to do more than that. I will also be able to see your drawings. I can go through the steps of your drawing, and if I have the time, I can make comments for you. If you are doing something wrongly or you can improve, I may be able to come into your drawing, and Fusion 360 gives us the ability to be able to, for me to reach your drawings as well as for you to reach my drawings if we allow that kind of collaboration to happen. So that would make it easier for you. And then there are certain homework assignments that are going to be special, because I know that students over the years like to copy. Some students are so lazy, they don't want to do anything. They just want to just change the matric number on the drawing and take a copy of it and submit to me. It's not going to work. It is good for me to tell you up front, it will not work with me. You are going to fail if you try that. Because I know enough about programming and the way this and then Fusion 360 is a time limited drawing tool. I can go through your steps. If your steps coincides 100% with another person's step, you have copied that person, and I will deal with that in a way that may not be pleasant for you. So don't do it. So what I would need from you are as follows. I need your complete name, each person. I need the email address that you use for your Fusion 360 registration. I will send you an invitation to join the online class. By online class now, I'm not talking about the class we are holding right now. I'm talking about an online class that continues after this class. That is, anytime you are doing your homework, anytime you are using Fusion 360, you may find yourself to be in class, because if I happen to be online at that point, I may just decide to look at what you are doing and talk to you, or at least interact with you. So it will allow me to view your drawings and provide feedback. Homework assignments will also be shared this way. You will soon see that the homework assignment I will give you before the end of the week, you cannot copy it. I will give, if I have 100, it's the same assignment, but there are 100 differences in the assignment. So your own will be different from the other people in the class. So you will not be able to just copy another person. You can be helped by another person to show you how you are to do something, but you cannot just simply copy his own. Because if you simply copy his own, your answer will be wrong, because the answer will not be the same. For any two people, everybody's answer will be different, and I'm going to check that. Now, I want these details provided directly in the chat room. Like I said, this will be the primary means of communicating with you from now on. Those that use other means more frequently, there are people who don't use their email that much. They use their WhatsApp numbers. Well, it is your business to tell what you provide for me. I need your email for sure, because it is your email that I'm going to use to access your Fusion 360 files. But because I'm also going to use that email to communicate homework assignments and other issues to you, if you know that your email is not your primary means of communication, that you do not check it frequently enough, you might also provide your WhatsApp number. That's your choice. The latter, that is your WhatsApp number, will not be needed if your email provided is a reliable means of reaching you. Note, there will be no excuses that you did not receive a notice if we can show that it was sent to you, to the contact you have provided. Because you are providing this contact to me, you can no longer blame your class rep or the admin, because you can only blame me. And it is not very good for you to be blaming me, because I'm the person awarding grace to you. If you are blaming me, then you are fighting the wrong person, because you are not likely to be able to win that battle. Okay, so that is the second thing. The third thing is that you should be able to use this to co-exchange comments when you are doing your assignments. I'm not 100% how it will work out, because this is the first time I'm doing this, but we shall try. Once I have your email addresses, I will set up the group. And Autodesk has assured me that that will work. We will be able to have a back and forth. I'm hoping this may lead to more constructive feedbacks on both sides. For example, it is okay for you to tell me what you think about the course. Tell me how the course is affecting you. It may help me to change things in your favor if there is something I can do. And if there's nothing I can do, I will let you know there is nothing I can do. But I'm not going to get angry because you tell me what you think about my course, whether good or bad. It doesn't. I know that it's not everybody that likes the way I'm doing things. So you are not the only, you will not be the only person. We will initiate a discussion in these first 10 minutes in the chat room, discussing how the course is going for each of you. Share your feelings and challenges can help me support you better. I will consider possible changes if necessary. I would like to understand how I can assist you further to enhance your professional development through this course by this means. The last thing I want to bring to the discussion is that I face challenges while simultaneously drawing and teaching. I keep going back and forth and saying too many times when I'm drawing and I'm telling you how to draw from scratch. I prefer to draw quietly when I'm not talking. I do better that way. But when I send you a video clip on your slide, that video clip probably plays well on your computer. But when I am trying to play that video clip over the Zoom, the sound quality is poor. So what I have done so far is that I just switch off the sound, I let the video show, and I talk over it. But I don't like that either. Since you typically receive the videos and the slides are sent, I spoke over the video, allowing you to view and prepare the video after class. Now, are you satisfied with this setup? I am not, and I will tell you why. But let us discuss it. So this is the basis for the discussion. You can type your discussion and let us see, because that way will be fast. But don't be slow, because we are eating into the class time, and I want to quickly go and teach the class. So let us see what you have to say in the chat room. Go to the chat room now. Provide me your details, and then give me your comments. I want both. Okay, I can see. Yes, you are providing things, but are you also going to attend to the other issues that I have raised? Nobody has made a comment on the other issues I raised. Did you hear me? Mario Wabuzo Chukudi, you have not done what I asked you to do. You have not sent an email address, the email address that you use to register the course, and register for your Vision 360. I'm still looking for the email address that you use to register your Vision 360. Adetola, Samuel, other people for the same thing. I still need your email address, Adetola. Yes, thank you for that comment, Okoyemi. Let's see what. Okay, I can see your comments, Olaoluwa, Emmanuel, and Okoyemi. I'm seeing the comments there, taking note of them. You have to save your work to Fusion Cloud. That is a Sulaimon. Why will you not be able to save your work to Fusion Cloud? Sulaimon, can you tell me why it will not be possible for you to save the work? I'm not saying you should save all your work. I'm talking of work relevant to the class, like your assignments and things that are for this class. Why will you not be able to save it to Fusion Cloud? Explain, Sulaimon. It doesn't matter, Daniel. Even if you are not, we don't have to be on the online together. I may just look at drawings you've already done. When I open your drawing, I can still go through your timeline. So it doesn't. In fact, we do not have to be on the. It's just that you may get the comments later. It doesn't have to be that we are doing the thing together. No, no, no. There's no problem, because you have your timeline, which I will see. Who is it I want to talk to now? Muslima, please check with the other students, check with your other classmates. They may be able to help you. Yeah, you can get, I can show you, I will give you much more than what goes on in class. For instance, there are some of the projects I will give you that will answer some questions like simulation. I will give you some of my simulation projects to see, because we are just in the first level. There are we can have 10 courses like this, and we will not finish the things that I do with Fusion 360. So it is a good idea. I will show you more than I can show you in class. That I'm answering Oluwashola, sorry, Ola Oluwalawa. Oluwa Pelumi, you will always have the recorded video. You will always have the recorded video, so that we're not going back on that. What I'm saying is that during the class time, I don't want to just be miming and lip syncing on it. I would prefer, what I'm trying to do, the change I want to make is that since I have already given you the full video, even if we don't finish it in class completely, or if I make mistakes in class, you can see the recorded one that I've already given you on your slides. Do you understand that? So Oluwa Pelumi, do you understand that? Well, don't worry, Kende. Just make sure that from now on, you will do the correct thing. I have not given any grades to the previous work. We are now going to seriously grade your performance from now on. The homework will be more serious than before, will be more specific than before. Kende, I'm answering you. So, you understand? But at the end of today's class, you can make your comment. Let us see what will happen today, because I'm doing it differently today than we did before. Yes, Olalu, I've already answered that. You can get access to extra projects that I've worked on. Yes, I said so. I answered you. Okay, I think we've spent enough time on this. We can go back to the lecture now. Please don't forget to give me your details, like I've said, and you can give me more feedback if you have them, and I will take a look at it. Then, okay, so let's go back to class now. I can make sure beat this down and get the slide and project from the current slide. Okay. Today, we are going to focus on pattern creation, fans, and multi-cylinder engines. We will use a fan to demonstrate the creation of pattern. So you see the reason why I'm bringing fans and multi-cylinder engine. A multi-cylinder engine is a complicated thing because each engine cylinder is itself complicated to start with. And then when you now make patterns of that to make a multi-cylinder engine, I want to let you see that you can do patterns from very simple things. That's why I'm bringing a fan. I will take a fan and we are going to use pattern replication to create the blades of the fan. And that's a very simple way. Then we will end the class with a multi-cylinder engine and you will get your homework, which we will discuss when the homework is due. I want to give you 2 weeks so that we can move on fast. I'll give you 2 weeks to do this homework, or maybe a week. I don't know yet, but we will see that. Previously, we assembled the crank, connecting rod, and piston created with simple cylinder an engine block parts into a single engine. We did several things, and then we made them up all into a single engine after making it a schematic cylinder and a schematic block. You can make the block as long as you create something that does not interfere with the motions of the moving parts and close it up. Usually what is done in a cylinder engine is that all the cooling infrastructure, like the pipes that would pass water or oil to cool the engine, would also go through the block. That's all that is really essentially necessary in the block. Then on top, you have the intake manifolds where you have your petrol and air coming in, or diesel coming in, diesel and air. And then your spark plugs are also on top there. And then your exhaust gaskets, then your exhaust gadgets that take the waste products out of the engine. If you can go to the internet and you can take a look at what a typical four-cylinder engine looks like, and you can do some. I will show you that you need to do a little bit of research, not a lot, a little bit of research to be able to do this work well. I will tell you a little bit more about the four-cylinder engine. I think today is our last talk about that. We are going to move to other issues after today. We are going to discuss the fan and end it today. Today is the last time we are going to talk about engines. We will be talking about other things like turbines and impellers and some other things like engines. We will be, because this whole course is going to be taught by examples only. We do not just teach anything in theory. You learn anything, you apply it, and you practice, and you submit a homework assignment. That's how, because the goal here is to build your skills. Build your skills. You are in 200 level. If you start with build skills at 200 level, by the time you are in 400 level, you should be earning income from your skills. And not even when you leave the university. So imagine what will happen to you when you're on youth course. So, and then you should be able to see how this course helps you in some other courses. I will discuss some of that with you, because if your graphics is good, it should assist you in your design and in virtually every other course you are going to take. We also learned why components are needed in the assembly. Bodies can be made in different ways, but they must be made into components in order for you to be able to assemble them. And that is because it is only inside the components that you can have joints. You cannot add a joint to a body. By the time you add a joint to a body, you're already having a component. So it is only components that can be assembled, because assembly takes place in joints. So we made relevant components and assembled them accordingly. We've done all this before today. So we're going to move from this today. Today we are going to introduce patterns. We shall introduce linear and circular patterns with simple practice. As usual, we will use simple practical examples that you must implement on your own, and show a simple way to make a fan blade or impeller of a turbine. The same method you use to make a fan blade is what you will use to make the impeller of a turbine. They are very similar. They are not the same, but they are very similar. These will later be examples when we introduce the application programmers interface Python programming, to show how more complicated designs can be achieved. The goal really is to take you to application programmers interface. So you are using not just the GUI to create your drawings, but you are programming Python to create the drawing. I want to get to that at all costs, for the simple fact that several of you will go into artificial intelligence and IT. And what you will do when you go in that direction is that you are going to be working with application programmers interfaces. APIs are essentially the same logic. It doesn't matter whether you are doing TensorFlow or PyTorch or any of the large application programmers interfaces that they use in machine learning. If you understand the application programmers interface inside Fusion 360, it should be a good introduction to that. So you need it. So we will go through that before the end of this class, no matter how short the time we have on it. But I want to do some basic examples first before we do that. Today we begin with a fan to show that we can do pattern replication of simple designs and drawings. Multi-cylinders engines show a pattern replication, the pattern replication of a more complicated primitive. So we also show you how to mix created bodies and solids. So we will surface created bodies. We create some bodies using surface. We create some bodies using solids, and we'll mix the two of them together into this class. So those are things that we will do. Forget about this page. I'm going to modify this page now because I plan to create the collaborative something. I'm not going to use the collab. I'm going to do it on the Fusion 360 on the Fusion platform itself, not just collab. I will show you how it works when we get there. I will give you details as to when your assignments, what your assignments should contain and when they will be due. And once you get your drawings to a particular place and I give you a go ahead, that means you have submitted. So there will be no passing things through your class rep and telling me your file was missing and all that story. No. Today's class will begin with the fan because the fan is very simple, easy. And in the fan, we are going to do two sketches. This one on the top right corner is just a single line, 20 units long on the x-axis. And I want to show you how I did it. Yeah, there are ways that are complicated, there are ways that are simple. So I want to just show you a simple way to do it. It's a very simple, trivial thing, but it took me some time to get the optimal way to do it, and I think it might be useful to you. We'll do two sketches. The lines created will be used to loft for the fan blade. The first line is on the YZ coordinate plane. It is 20 millimeters long. We constrain its center to the origin and we end the sketch. Now, I will go to a fresh Fusion 360 page and I will show you the way you can do it that I don't want you to use. And then I'll tell you the way I want you to use. And then we'll move on. And then maybe this is the second line will be on the construction plane offset between 90 and 100 millimeters from that place. And you'll see that this is, even though you see it's a single line that is curved at the origin, they actually started their lives at two lines. One line was 15 units to the bottom there, to the left bottom, and then the other one was 20 units to the left top. The curve you are seeing here is a fillet. It's a fillet that joins the two of them because I wanted a continuous line. I didn't want the angle at that point. I'll show you how that is done, and then from there we're going to loft it the way I've already described in the video that is on your slide. But this way, let's just do it now. I'm going to do it from scratch here. So to do it from scratch, so we are going to leave the slides now. We are on slide 11. So we'll come back to slide 12 or 13 when I'm done. So let's go down. And now we choose our Fusion 360. Now let us start with a new page, a new drawing. So what we are saying here is that you just create a sketch. You create the sketch is now on the YZ plane. And the first thing you do, you draw a line. When you draw a line, you put a point on the line. So you create a point. You create a point somewhere on the line. So there's a point on the line. The next thing you do, you make that point to move to the, you take that point, you put it at the center of this line. So that point now has been in the center of the line. It doesn't matter the length of this line. If you like, you make the line longer. You can take a dimensioning tool and make the line longer. Let us say you make the line 100 now. That point will always be in the center of the line. Even if you move the line away, somewhere else, and you reduce the length of the line. Let us say you reduce the length of the line to 40. That point is always at the center of the line. But I want that line to be 20 units. I want it to be 20 units long. So the next thing I want to do is to make the center of the line coincident with the origin. So I will say coincident. I'll choose the coincident constraint. I want this center and this thing to coincide. So you can see I brought the line to this, and the center is at the origin. The next thing I want to do, I want to further constrain it to be horizontal. So I constrain it to be horizontal, and that is it. So that is how I want you to draw the line. So the line is there like that. Well, if I want this, there are other ways I can do it, but this is more efficient. I could do it by just first of all drawing one line. I can draw one line from the origin to the left and say, okay, and I can make that line itself, is it already horizontal? No, I can put the horizontal constraint on it. I can put the constraint so that the line is horizontal. Okay, it said it's already over constraint. So that line is horizontal. Oh, of course, I can come and do a mirror. I can do a mirror of the line and select the line for mirror, and then select since this is the YZ plane, select the Z axis as the mirror line. So if I select the Z axis as the mirror, will that be okay? If I say okay, so you can see, and I can now come and dimension this line. I can take the line. I can now dimension this 10. So if I dimension this 10, wait, what have I done now? We'll undo. Okay, maybe I should have dimensioned it first. I can dimension it 10. 10. I can still mirror it. I can still mirror it, then it will be 10 on each side. But I don't want you to do that. So I'm removing that line completely. So I think it is more efficient, not a matter of my preference now. You can use whichever one you like, but I'm just saying that it is, because this is still a single line. So that is that. So if you're happy with that, you can say finish sketch. The next thing we are going to do is to create a construction plane. It's an offset plane. It is the same YZ plane, but it's now offset, say, at 100 units. Okay, so that is okay. So we are now going to choose that. We are now going to do our next sketch on that construction plane. So create sketch on that construction plane. The sketch we are going to create will be 2 lines. So we start a line, say from here to the origin and to a different angle. And then if we are happy with that, we say we accept that here. So that is accepted. Now, what we want to do, I want to create dimensions now. I want this part of it to be 15 units. And I want this part of it to be 20 units. Then I want the angle. I want this angle. So I again turn on the origin. I want the angle between here and this axis here. I want that angle to be 15 degrees. I want that angle to be 15 degrees. And I can move that 15 degrees. So I want this angle here between this line and this axis. I want the angle there to be 40 degrees. So, and I want now, if you let us look at it, you can see that this line is having a sharp turn here. I don't want this sharp turn. So because I don't want that sharp turn, I can put in a fillet there. I can choose my fillet, and I want to fillet between this and this. And it is a fillet. I want a fillet of 40 radius 40 fillet. Okay. So with that, this is radius 40. Okay. That fillet line there is of radius 40. When I'm happy with that, you can see now you have this line is smooth in that place, and say okay. So the next thing I want to do, I don't need the origin to show again, and I don't need the sketches any longer. Oh, no, I need the sketches. It's just I need the sketches. I don't need the construction line. I don't need the construction surface again. So what I want to do now is to go to the surface, mode, and I want to do a lofting. So I want to do a lofting. So I will choose a loft. So the loft now, I can select this original line now. That is one. Then I will now select this. This line has 3 sections now. So I will select them one by one. And I will loft. So, and that is creating a new body. This body is not the same as your solid bodies because there is no thickness. It is just the skin that we have done. But you will see what we'll do with that skin later on. I can click OK, and then I can go back home here, and then if I like, let me just take this thing. This thing is disturbing me here. Let's see if there are some things about Zoom that are okay. Yes. Okay, so I can, you see, this is the loft, this is the blade, this is what I'm going to make my blade out of. Okay, so let me go on now. From there, I can say from this, I can go home. I can go home, and what I want to do next is to create another sketch. I'm creating a third sketch. Create sketch. The sketch I'm creating now is on the XY plane. And let me bring the whole thing in here. On this XY plane, there are two things I want to create. The first thing I want to create is an annulus. So I can create an annulus here. Maybe the first annulus diameter is like 10. And then I now create again, repeat the circle. And the second one is like 25. Okay, so I have this. So this is an annulus, and you'll see what I will do with that annulus later on. But 2 center diameter circles at the origin will give us that. Now, what I want to do next is to create a spline. I want to create a spline here. So I'm going to start my spline somewhere around here, and I will make a spline. I'm happy with that. So the next thing I want to do is to mirror that spline. So I create a mirror, and the mirror is the spline, and then the mirror line is this axis. Let us bring back the origin. The mirror line is this axis, and you say okay. Okay, that is the mirror line. Now, if let me hide the body, you will see that there are some problems around this point. The problems around this point are that the 2 lines are maybe they are meeting at a point there, and but they have different tangents, and I don't like that. So in order to solve that, I can create a fillet there. I want to create a fillet between this and this, and I want the fillet to be that fillet is not working. Okay, let me try and do a coincident. I want the 2 points there to first of all be coincident. I want to choose, no. In this sketch, what I want to do, I want this and this. Let me try the fillet again. It's between this and this. Yes, the fillet is better now. So you can create a fillet there. So when we create that fillet, it's let me make it 8 units. That will be the radius of the circle there, the radius of the arc there. So when I'm happy with that, I click OK. Click OK. And then I think one more thing I want to do, I want to close. Well, perhaps I don't even need to do any closure again. So this might be okay because everything that I need is on the same plane now. So let us see what we do next. Finish sketch. So that sketch is done. So what I want to do now is to bring back the blade that we created before, the body that was there before. And still on the surface, I'm going to do a surface extrusion here, create an extrude. I want to create this, I want to extrude this. I want to extrude this profile and create, what should I create? A new body. I want to create a new body. And I want that extrusion to be on 2 sides. So I move it up and then move it down. I'm only making sure that it cuts through the original blade. So when it cuts through the original blade, I am satisfied. So I can click OK. So with that, the next thing I'm going to do, I'm going to do a trimming. This trimming is different from the trimming you've been used to. This is a body trim now. So I will say trim. The trim I'm going to do here is asking me to select a trim tool. I'm going to select this surface profile as a tool. And then I'm going to select the fan blade itself as a trim tool. So when I'm happy with that, click OK. I'm going to hide that body. And once I feed in that body, let us go home now and see what we have. So let us do an obit. So this is the fan blade. This is the blade of the fan. This blade of the fan has no thickness. It is just the surface. It's just the skin of that blade. Now, you can do better now. We can now put some thickness on this. We can put some thickness on this. If you right-click on it, we can say thicken. In the dialog that ensues, we can thicken symmetrically. And let us thicken it to 0.5 of a millimeter symmetrically. So that is the blade of the fan. And what can we do? Here, at this point, we are in a position to do a pattern replication. We can create a pattern replication in the, I prefer to do it in the solid body. So we can create a pattern replication. So we go from create, you do a create pattern. Here, I want a circular pattern. And I want a circular pattern. I want this body. It is this body that I want to replicate. And it's asking me for an axis. I want this Z axis. And let us go home now and see what it has given us. No, I want to pan that. So you can see the blades here. If I want to orbit this now, you can see the blades of the fan. If I choose 4 blades, if I choose 5, if I choose 10 blades, if I choose 10 blades, this again is this is a fan. If I decide to choose, I can edit that. I can edit that body. Let's see where it is. Let me take this thing away. That pattern. Where is the pattern? Okay. I can edit the circular pattern. I want 3. I can choose 3. So you can see that when I'm creating a pattern, I can choose the number in the pattern. So you can see it's as easy for me to choose any number that I like. So here I have 3 of them, and they are as shown. So the next thing I want to do is to go back to our sketches. Can go back to our sketches, and in sketch 3, I am in a position to now create a rotor and a stator. Normally in a real file, you create only a rotor there, but I'm going to create a rotor and a stator because of the assembly process. So I can create an extrusion in the solid making body now. I can create an extrude, and I created an extrude here, and I said I want that extrude to be symmetric. I want it to be symmetric, a total thickness of 5 units, and it is a new body. It's not a cut, but a new body. If I'm happy with that, I click OK. So that is the rotor there. I can make all these ones into a component. So I can create, in order to make it into a component, what I'm going to do is to combine the 4 things. Combine. I can combine everything into the rotor. That is 1. And then I choose the blades one by one. I've chosen 3 blades. And if I'm happy with all of that, I click OK. And that is now a single body. So these 3 blades and the rotor now constitute a single body. I can make that body into a component, create a component out of it. If I create a component out of it, I can name that component the rotor. That the rotor, that is the rotating element in the blade, is here. I just call it a rotor. I call the whole thing a rotor, and that is it. So that is now my first component. I can take that off and turn on my sketch again. I want to create a stator just for the purpose of this fan. So I say create another extrude. I take the extrude from there. Again, I want it to be a symmetrical extrude. And I want the total distance there, the total thickness there to be 6 or 7. Or let us make it 7 units. And I'm not creating a new body here. I'm creating a new component. And say OK. So that component, I'm going to call that component a stator. So you can see that from there I can turn on the rotor again. So both of them are on now. And I can go now and do an assembly of what I have. I can do an assembly of the rotor and stator, and I can say assemble. I can use an as-built joint. Assemble. As-built joint is asking me for the components that I want. One of them is the rotor, and the second one is the stator. So 2 things have been chosen. It's asking for the snap. Now it is. I want the rotation to take place around this axis here, and it's a revolute thing. So click OK, and when I'm happy with that, I can go to the joints. I go and look at my joints. It's a revolute joint. I can animate them. Let's see, revolute joint. Okay, so the animation of the joint is like that. So that is the fan that we have made. We have made that fan. Let's see how much time I have. We have made that fan through the body replication process, and that's a very simple thing. And now we have made a very simple fan. There are so many things you will notice. We arbitrarily just decided on the angle of bend, of tilt of the fan, the length of the fan, the number of the fan. The question I want to ask the class, what we have just finished doing, have we done a design or have we done a drawing? I want you to go to the chat room and answer me. Did we just design a fan or did we just draw a fan? And please, as much as possible, give me your reasons, because this is central to your training as an engineer. And this is also central to what an engineer is supposed to do, because you are in a society that is so sensitive to theory, and it's only if you manufacture, if you make a tire or you weld two things together, that's when you are an engineer. But I just want to ask you, what have we just done? Have we drawn or have we designed? And the answer will help me to instruct you further. So I am going to go off this one now and go to the chat room. So we're in the chat room now. Please begin to give me your, and now please be fast with your responses, because we still have a lot of grounds to cover for today. So I don't want us to. Okay, Opayemi says a design. Olokwade says a design. We have designed a fan. You have designed a fan. It's a design, sir, because we just modeled a solid body and so do a rotation. We designed a fan. We designed a fan because we took account of technical aspects. Okay, that's a good feedback. But let me disappoint you. We have not designed anything. We have just drawn a fan. We have not designed. We have not designed. Let me tell you when this thing will become a design. We have not designed a fan. Let me write that down so that we did not design a fan. We only drew a fan because we saw one before. Let me now tell you, yes, Oladapo Salami, you've got it. We just drew a fan because we did someone else's idea. It's a drawing. It's just a drawing. Now, let me ask you the second question. What will have to happen for this to be a design? What must happen? When does this, what can make this a design? Go back now and tell me what will make it a design. Please be very frank, be quick, and then I will tell you the things that will make it a design so that you can situate what you are learning now, so that you can know the other things you need to learn before as you are going on, because you are in 200 level. If you know the things you need to learn, the kind of engineer you will be by the time you are graduating will be completely different. If you don't know what you want to learn, then you will just be beating about the bush. So let's see what I want to see. Ideate new changes. Ideate. I don't even know that word. Emmanuel Ogbaji, you are teaching me something. I don't know the meaning of ideate. I only know simple English. If some things have been modified, well, Fatima, you are right. Yes, specifications. Somebody is talking about specifications. You are beginning to say, and after doing our own research, it's not research. You will see what you need to do. You would modify, you do specifications. When we take all the perspectives of a working fan into design and action, changing the specifications may be more blades of different sizes. We need to design to actually solve an actual problem. Components of the fan done with our ideas. It will be a design once the idea can be implemented. We make a specialized model of the parts. We need to make a fan to perform its function to be a design, and so on. Now, you have the general idea, but this is my duty as your coach. I say I will coach. Let me tell you why. That's how I see myself. As I am retiring from the university, I ask myself a question. As I've been teaching for many years, I don't need to bother you with how many they are, but I've been teaching for many years. And the question that comes to my mind is that, am I a storehouse of knowledge? The answer is no. I'm not a storehouse of knowledge. There's much more knowledge on the internet, on your phone, than 1 million of me put together. So we are no longer storehouses of knowledge. That when I was at your level, I used to see my lecturers as storehouses of knowledge because they had knowledge that I could not get from anywhere except through them. But today, you don't need us for knowledge. Not at all. If all you need is knowledge, then your AI and your internet and they'll give you all the knowledge you want. What we are coaches, because I am ahead of you. There are things I know that you don't know. There are things I've experienced you have not experienced. And therefore, I can guide you into the storehouses of knowledge. So I'm your guide and coach. So what your coach is going to tell you today is to tell you what really is a design. And to tell you what a design is, let us take this fan. And let me tell you, let us go back to the fan. I'm going to leave the chat room now, but you can continue posting things there. I will read the things you post there later on, even if I cannot continue looking at it during the class. Let us go back to the fan. Now, the person who will buy this fan, what does the person want? The person wants some comfort, and the comfort will be obtained by an amount of air blowing at him, which will be more than the air that naturally blows. That is what he wants. He wants this thing to blow some. What other thing does he want? He doesn't want the thing to consume too much electricity. He wants the thing to make him comfortable without consuming too much of electricity. If you do not satisfy those two conditions, even if you make your fan and the fan works, he's not going to buy it. You can make 100 and you carry the 100 to your house and it is a failure, because the reason why there is an engineer is that the engineer is able to persuade somebody else to buy the product. You make a product that somebody else will be persuaded to buy. It's not just for you, it's for the public, it's for the consumer. So if you cannot do that, you have not designed anything. You have just wasted your time, and you'll be sacked by your employer anyway. Now, what you need to do is to see how to optimize these blades so that you can drive an amount of air that will make the person comfortable at the price he can afford. So you will need to know how many blades you should use, because the more blades you use, the more money you spend. If you use fewer blades, you are going to spend less money. But if for instance, you cannot use one blade. And let me just go back to the chat room. Can you tell me why the fan cannot have one blade? The fan cannot have one blade. I want to know whether you know why it cannot have one blade. Why is it that the fan cannot have one blade? Let me hear you. Let me see your comments. I can see Opeyemi. Nobody else wants to talk. Why is it that the fan cannot have one blade? Okay. Yes, it cannot have one blade because there will be out of balance forces that will wreck the thing holding it. It's not going to be efficient. It will be vibrating and it is going to spoil very fast. Okay, so we know it cannot be one blade, but it can be two. But you see that most fans have more than two blades. Why? Don't they know that they can save money by just putting two blades? And there are many reasons why the fan may have more than two blades. Now, what about the angle of orientation? Should it be flat or should it be tilted? How tilted? Now, when you come up, let me now tell you when your drawing becomes a design. Your drawing becomes a design when you can answer the question, what are the number of blades that are optimal to perform a particular amount of airflow? When you can answer that question, then you are designing. You might be copying some ideas, but no matter how you get it, you are answering the question, how many blades should I use? what should be the shape of the blade. You don't just do it arbitrarily or because you saw it somewhere. If you tilt it in one way, what if I change the angular orientation a little bit? Why should somebody buy your own and not mine? You must prove that your blade orientation, the length of your blade, the size of your blade, they optimize that flow of air. How will you ever get to know that? There is a course called fluid mechanics. That is what fluid mechanics is about. If you are able to bring the knowledge of fluid mechanics into your design such a way that without even making anything, you can simulate this fan, you can calculate how much air it will drive, and you can change the blade and see how the amount of air it drives changes, how the resistance to the rotation changes, which tells you how much power you need to drive the fan. And then by the time you can get optimization of all those things, and you now design the length of, you now do the length of your blade, the geometry of your blade, the orientation of your blade, the number of your blade, as a result of the theory of fluid mechanics that drives the fan. When you can do all of that, and you now arrive at a fan that can be manufactured and can be sold, then you have designed. So what it means is that the drawing you are doing is just stage one in the first baby step in a very long process. So let me first of all go back to the chat room and see whether you have questions, or you can tell me, you now appreciate the difference between the drawing and the design. Do you think? No, you don't worry. Do you think you now know the difference between the design and the drawing? Okay, Okoyemi, I can hear you. So you can see that the fact that you draw a very good blade, very good fan, and you know auto fusion 360 very well, you have not designed anything. You have just drawn. You have just drawn. Now, so do you now understand why there is a course called mechanics of fluids? Do you think you understand why there's a course called mechanics of fluids? Do you think you now understand why there's such a course? Because mechanics of fluids will guide you to now use the theory, the equations. The mechanics of fluid will give you all the equations of motion of fluids through anything, and you will be able to see how the fan can drive air, can drive, if it is an impeller, it can drive water or some other things. It's not, your work is not done. Your theory is not finished. There is, suppose you get an optimal fan. Suppose you have a fan that is optimal, and as you turn it on, the stresses created by the air creates a crack on one of the blades, and after 3 weeks, the blade falls off and cuts somebody's neck or somebody's hair. Are they going to call you at work and give you a promotion? Is that what they're going to do? Is that what they're going to do? If there's a crack on the thing as a result of, Adeyemi, you think they will give you, Adeyemi, you really believe they're going to call you at work and give you, they are going to fire you, if not sue you also, in addition. So that is why you have a course called strength of materials, which will now calculate, as the fan is moving, how much forces, how much stresses are experienced by the blades, especially where they are joined to the rotor. And we'll calculate whether the dimensions you have chosen will be enough to carry, given the material, to carry the load. So you can see now there is a combination of fluid mechanics now with strength of materials. Okay. I can't understand, sir. My network kicked out earlier. I can't understand. I don't know what you cannot understand. So what do you want me to do? Okay, so what we are saying here is that there are, I can give you, there are at least three courses called mechanics of. All those courses are to be added to your ability to draw for you to be able to design. Let me tell you what the bad news is. The bad news is that it is very difficult to bring all these things together to get your blade to get your blade profile. The good news is that with a software package like Fusion 360, you have all the equations you will learn in University of Lagos are already programmed inside it. Yes, well, thermodynamics may be needed, may or may not in this particular case, but that is part of it. Now, all the equations we learn in Unilag have already been programmed into Fusion 360 simulation package. So you will now use that simulation package to invoke those equations. And there is also Autodesk fluid flow or something, or you take it to a fluid flow simulation package, and you'll be able to now optimize. You'll be changing the blades, optimizing the blade until you get an optimal one, and you see the amount of energy you need to drive the blade. And then, so when you finish the simulation of it, you will have answers to all the questions we asked earlier. When you have those answers, and you now do a drawing of a fan that has answered all those questions, do you now understand that at that point you have a design? Okay, so that is how you design. Now, that begs the last question that you will ask. How does the simulation package do all these things? How does it do all these things? The simulation package will do these things this way because the blade of your fan and the environment where your fan works is a very complicated boundary condition, which the equations you are going to solve when you are in secondary school and first year, second year, you are going to be doing mathematics. You get a function, you differentiate it. The functions are well behaved. They have nice turning. You know, the room where you are going to put the fan is not a well behaved function. It has sharp walls and all sorts of things. So your equations that you learn in the textbook they are not going to work. It's only numerical solutions of those equations that will work. And the software packages you have, like your Fusion 360 and other simulation packages, already have finite element products that are essentially numerical solutions to those equations. So the minimum you will learn is how to build those equations, and then you might learn how to make finite elements out of them. But you will not need to do that yourself because the software packages that simulate will help you. But you will need to understand those equations to be able to make sense. To communicate with them, you will need to understand those equations. That is why we did not send you to a mechanics workshop because you want to become an engineer. We are not making fun of mechanics workshops. The mechanics are providing excellent service to Nigeria. They are perhaps the only people really working. The rest of us are just changing papers and building 750 duplexes by just altering papers and such things. So what I am saying is that if you want to be a motor mechanic, go and be a motor mechanic and you can live well. But you are not therefore a designer. If you are a designer, you will have to understand a lot more theory than the Nigeria has appetite for. The people who do the greatest amount of theories in the world are the people that go to the moon, that go to Mars. The amount of theory they do, they talk in several dimensions. In fact, the theory they do will break your head. So theory, we are not doing any theory really in Nigeria. We have not started as far as theory is concerned. But I'm just telling you, it is those theories that enter the finite element packages in your simulation package. That is why you can design. I will try and share a project of a student that designed a group of students that designed a fan in the competition we did about 3 or 4 years ago. And that's a very good, you will see how he arrived at the number of blades of his fan and all the simulation he did. When you see that, you will now see the difference between designing and drawing. And so just understand that where we are at right now, we are at the beginning of that process. I think I've talked enough. It's 9:11 now. I will give you a break of 15 minutes so that by 9:27, not 9:30, by 9:27, we are going to continue this class. Thank you. Before we went on break, remember, we went through the blade of the fan by creating 2 lines, which we lofted in this surface mode. And we did these 2 sketches. You remember how we did the first sketch, created an arbitrary line, put a point at the center of the line by constraint, and constrain that point to be at the origin, and then make the line horizontal. Then we ended that sketch. And then after that, we did 2 lines, one 15 units, the other one 20 units, at a sketch plane that was about 90 to 100 from the origin, along the same YZ plane, but offset by a number of units. And when we did it, we did a filleting at the origin, which created an arc that went into those lines. And you can see something like this was done. We did that. Then after that, we went and created this loft. We created the loft between those 2 lines. And after creating that loft, the next thing we did was that, let me just put a slideshow from here. So the next thing we did was to create a profile. We create a profile, and then after creating that profile, we use that profile as a cutting tool to cut the blade that we created before. After doing that, we now went and created our assembly, and did that assembly in a way similar to it. I have a full video of it, which is already on the slides that I shared with the class. I'm told that those slides are with your class rep, so you get them. So if the Zoom video is not fantastic, I'm hoping that the one that was on your slide will make up for it. So that is so I'm not going to go through this and mime it, because the video, the audio is not good. So we did this. We can do a single blade. We can do a pattern replication and do as many blades as we want. And then we also made the rotor and the stator so that we can do the assembly very well and create a motion that you will see. So that is, again, a full video for that part of it. So, but I don't need to go through this since we've already done it. So we are going to the next thing on today's agenda, which is making a multi-cylinder engine from the single cylinder engine, multi-cylinder engine. Now, before you make a multi-cylinder engine, let us assume that we are dealing with 4-stroke engines. And in a 4-stroke engine, there are 2 crank rotations between the firing in each cylinder. Because a 4-stroke engine goes through 4 reciprocating motions, which constitute 2 cycles of reciprocation. And 2 cycles of reciprocation is equal to 2 full revolutions of the crank. And if 1 revolution is 360 degrees, 2 revolutions will give you 720 degrees. And if you want to share those 720 degrees among 6 cranks, that means that each crank will have 120 degrees to itself. Otherwise, you will find them firing at cross purposes with each other. If you want them to fire in an orderly manner and you gain all that energy, you have to divide the 760 degrees of fire into 6. So each one has 120 degrees inside which it can fire. Because of that, very many engine manufacturers use what we call firing orders. I want everyone to go into the internet, go and look at firing orders of common 6-cylinder engines, and you will come up with the numbers. Today, I'm going to use the 163542 firing order. And because I always want to concretize and be specific. So if you have a particular firing order, how will the crank angles be oriented? When we know that, we will orient the crank angles accordingly. Now, in a 16352 engine, the first cylinder to fire is number 1. And if you add, if 1 is at 0, the second cylinder to fire is number 6. If you add 120 to 0, you see that number 6 must fire at 120 degrees. The next one to fire is number 3. If you add 120 to 120, you get 240. That is why number 3 has the angle of 240 in rotation. The next crank to fire is crank 5. Sorry, is cylinder 5. And that is at 120 plus 240 will give you 360. So the cylinder 5 is oriented at 360. The next cylinder to fire is cylinder 4. When you add 120 to 360, you get 480. And the last cylinder to fire is cylinder 2, which is add 120 to 600, to add 120 to 480, you get 600. So the absolute firing angles per cylinder is 0, 600, 240, 480, 360, 120, in order to implement a firing sequence of 163542. You go read about this thing, and you can use AI tools to also get more information. But and then I want you to also do some research, because when I will do some things for you, and the grade you will get depend on how much other knowledge and other innovation you put in your drawing. So if something is 100 marks, if you just do the normal thing, you get maximum you are shooting for is 70 marks. The remaining 30 is going to be given to people who show some innovation, some further research, and the fact that their minds are active and they are getting information, more information than they got from me in class. So just know that this is how it is done. The last column here is talking about base angle. Angle 0 is 0. The maximum angle you can get is 600. So you have to subtract 360. And it's 360. So you have to subtract 360. So you are the one that is going to fire at 360. You put it at 240, but it will fire it will go through one round without fire and fire the next time. So it will, first of all, idle in its first 360, and it's only after adding 240 to that, it will fire. So the third angle will fire at 240. So if you look at the crank, with a layman's view, you would think cranks 2 and 3 are firing at the same time. They are not, even though physically they are oriented at 240, but the 240 here is 240 plus 1 cycle, whereas this 240 plus 0 cycle. And then the fourth cylinder is firing not at 480, but at 120, 120 plus 1 cycle of 360. And the fifth cylinder would be as if it is at 0, but it will not fire when the cylinder 1 is firing. It will fire in the next cycle, which is 360 added to it. And the sixth is at 120. So these base angles are going to determine your crank angles. So this is the cylinder. The firing order determines the absolute angle. The absolute angle, you remove 360 when necessary to be able to make sure that no angle exceeds 360, because you cannot orient anything at any angle outside 0 to 360. So you can add 360 to it by making it idle once. Even if you have 1,000 angles, you have to remove a multiple of 360 until you have something that is less than 360 that will now be your base angle. Which, because even though you know the absolute angle, it is the base angle that you will see. The absolute angle will be implemented through the your spark plug timing and all those things. So in the first cycle, there will just be no spark. When this other one reaches 240, there will be a spark here, but there will be no spark here. That's all. So that is how this will work. So let us now go into, I also did some research and I found out that the 163542 is characteristic of PRV V6 engine. And there are engines, the engines that use that sequence are DeLorean, Renault, Peugeot, Volvo. There are some American vehicles that also use the 163542. So that 163542 is a common configuration among vehicles for firing orders. When we are going to, by the time I tell you to do your own engine, I will give you, every student will have a different firing order. So your cranks will be different. So you cannot copy somebody else's crank. You get 0 because you will not be drawing your own crank. I'm going to give you, everybody will have his own firing order. And for your information, even if there are 700 of you in class, I will give you different firing orders to each student because there are 6 factorial number of ways I can create firing orders for a 6-cylinder engine, and you are not up to 700. So everybody in the class is going to get. So if you are thinking you will copy somebody else, better forget it. It's not going to work. It's not going to happen. And you are going to get 0 for doing so. But just do your own work. Get as much assistance and help from your friends, but make sure that the work you submit is your own work for your own answer. And it is me that will give you your firing order. So it is not the admin or the class rep. I will supply your firing order directly to you. And then when you are going to do a fan, you will have to get permission before you do your fan. You will take a photograph of the fan you want to do, and I will approve it before you do it. So I will approve specific fans for specific students. If the different fans are too similar, then we'll go and do impellers and some other things. So when we are going to talk about fan, you can do the fan of a computer, you can do the fan inside a motor car engine, or so you will just go and keep looking. So you must submit to me at least, each person will submit at least 3 fan pictures. Then I will pick one. I will tell you which one to do. So that's how we will do it. Because I want to make sure that we discourage outright copying and there's unseriousness that comes out of that, because it takes me a lot of time to prepare for this course. And I don't want any unserious student. If you're not serious, I'm not going to have anything to do with you. Okay, so we are going to do the engine now. It is necessary to modify the single engine we created earlier so that only repeating periods show. One rotor and one engine block is hidden, so to have a repeating pattern as shown here. The crank body may require splitting to make this happen, and the block body exists in 2 separate halves. I think I will go again and do so. After some time, we are going to do a replication, a pattern replication. This pattern replication will not be circular. It's going to be a pattern replication in, rather than being circular, it's going to be a rectangular pattern replication. And then when you create 6, it will initially look like this, but this will not work. We have not applied the crank angles. So these cranks will be oriented with respect to each other. And that is how you get your realistic crankshaft. To assemble the cylinders, we need to show, we need to apply 5 joints that are already established for 1 cylinder. We will rotate each, not cylinder, we rotate each crank in accordance to the firing order as computed previously. You saw that spreadsheet that I did to compute the firing order. It is after each rotation that we can apply the rigid joints among the crank periods to form the crankshaft. Now, there's a full video of close to 20 minutes where I explained and demonstrated how it is done. But in class, I'm just going to show you a few things. I will go and fire up my Fusion 360 and show you some of it now. So let us go there. You have, if I make mistakes in class or I have too much hesitation in talking, don't worry, go to your slides. You will see everything properly demonstrated there. So let us close this, bring it down, fire up the Vision 360 page, and then let me look for the new assembly that I did. Where is new assembly? Okay. So if you look at this, you can see that the crank angles have been implemented. This is the one that is 0. This one is 240. This is 240. This one is supposed to be 600, but when we subtract 360 from there, this one is originally 240. So these two look as if they are the same. This one is 120. You can see that whereas this crank, this connecting rod is in the forward position, the connecting rod there is in the backward position, even though the height look the same. This one is 360 degrees. It looks as if it is 0. And this one is another one, which is 120 plus. That's 480 or something like that. So you have this. I will show you what I will do. I will show you how to do one of them, and then you can do the other ones because it's a repeating pattern. To do that, let me save this as a new file. Let me save this as a new file, because if I save it as a new file, I can wreck that file without new assembly in class. Save. Okay, so this new assembly in class, what are we going to do about it? Let me first of all see whether I can just go through the video of it, and then you will see them one by one. I can take any one that is difficult. I will demonstrate it in a spreadsheet. Okay, so let us see the first situation. Okay, so this is showing how the single crank and the single cylinder was assembled. Let me go back again so that you will see it. You will remember that we started with a crankshaft, a crank, and then we bring in the connecting rod into it. And then after that, we bring the piston, and then we assemble the piston with it. And then after the assembly of the piston, we created a schematic of the cylinder, and then we move on from there. And then from that, we can do a pattern replication. So I want us to pause here. So let me go back. Now, this in the engine, this is the repeating pattern. We have to remove what was here for you to get that repeating pattern. And I think that is very important. So I'm going to show you that. Let me just fire up the new crank and take a copy of it and show you how to do that. So let me save this as new crank in class. Save as new crank in class. Save. What I am saying, you can see that this one has a rotor on this side, but it has no rotor on this side. But we have a problem. It is difficult to remove the rotor here. Let me tell you why it is difficult. Why it is difficult is that the way, if you look at the bodies make up here, you see body 1 and body 2. Oh, okay. We've already done that break here. If I don't do that break here, the whole body, I want to show you how I got 2 bodies let me combine these bodies. I want to combine. body 1 and body 2 into body 1 and body 2. I'm sorry, target body. Okay. Okay, so when we start, this crank, everything there is a single body. If everything here is a single body, you cannot just come now and remove this, because it's part of, you can't remove it, even though it is not, if you want to, but if you want to do a pattern replication, if you have something here, then it will be on top of each other, because you need to remove this, because this is the period of the engine without that other rotor. So how do we do that? We do that by turning this single body into two bodies. How do you do that? You do that by saying split body. Okay, so you are going to choose split body. This is the body you want to split. And it's asking you for the splitting tools. What are the splitting tools? The splitting tool is this surface, the surface of this place. That's the splitting tool. So if you choose that as a splitting tool, it shows you that it is going to cut this one off. If you say it's okay, immediately it turns this thing into two bodies now, not this body and this body. So that is the first thing you will do in order to get this kind of result. So what you then do next is that you hide this body just by switching it off. So you can see how a single-bodied crank can be turned into two bodies, and then you pick what is repeating, what the repeating pattern is out of it. So that is the first step we had to do, we had to take. So the next step to take is to now make a replica of this by doing pattern replication. So we are now going to create pattern. Create pattern is a rectangular pattern we are going to create, and then we are going to create it out of components. We are going to create it out of components, not out of bodies, out of components. And it's telling us to select the components. One way to select the components is to select the components using a fence. So if you use a fence like this, that you can select the components. So there are 5 components selected, and they are the crank, the block, the connecting rod, the piston, and the cylinder. So all those ones have been chosen. And then you are now asked to select you are supposed to select the axis of, the pattern. The axis of the pattern is the x-axis. So this is the axis here. We can either choose it here, or we can go to the origin of coordinates and select it. So we have selected the bodies, we have selected the axis. We now are supposed to select the distribution. I want the distribution to be done in terms of spacing, not in terms of extent. So in terms of spacing, I've calculated the breadth of the rotor and these legs, and then the big end of the crank, and this, everything is 130. You have to do the calculation. It's 130. So how many do we want? We want 6. 6 on one direction, and we want 6 in one direction, and we want 1 in the other direction. So that is it. So if you're happy with that, you click OK, and that is how we get our 6 cylinders through the pattern replication. You can see that just as easily as we did a pattern replication for the fans, we could also do a pattern replication for something like this. So if you do this, you can see the pattern. There are 6 of them now. The only problem is that if you check this one out now, if you are to, the joints that we have here are all belonging to the first one. So if you animate one joint, if you are to animate the joint, what do you have? If you animate the joint, you can see that only one of them is moving. The other ones cannot move. So because all the joints we had made pertain to the first one. So let us do the exactly, I hope in the class now, we can do the joints for the second one. If I can just pay attention as to how it is done for the second one, because we are going to replicate it. The only thing that we change is the crank angle that we calculated before. The crank angle for the first one is 240. So let us see how we do that. The first thing is that we create a joint between the connecting rod head and the connecting rod body. So we are going to do assemble, and this time it is convenient to use the as-built joint because, and the first thing is going to be a rigid joint. So this connecting rod will be rigidly joined with this head. So, and we select the two of them. We go to the number 2. Let me turn off everything apart from the joints. So we go to block 2. Let's see. Connecting rod 2, con rod. Let me see. You have 1, 7, 8, 9, 10, 11. Okay, so it calls it 7. So we go to the connecting rod there. We open it up. We are going to do the connecting rod body and the connecting rod head. Those are the 2 components. And then you can see that every other thing is grayed out except those 2 components. If you click OK, it has done that. We can go to the joints and test that joint. The joint we have just created, let us animate the joint. You can see that those 2 are now rigidly joined together. It shows that if they shake together. If they move together. Nothing can separate them. The next thing we are going to do the same thing in the piston. We are going to take the piston and connect the piston to the piston pin. So we go to the piston, and then we open it up, and then we say assemble as built. We're going to take the piston and the piston pin. So this is the piston here, and this is the piston pin pertaining to this cylinder. So when we are okay with that, we can test the connection and say animate the joint. You can see the piston and the piston pin are joined. The next thing we want to do, we want the big end of the crank of the connecting rod to rotate on the crank big pin there. So we're going to now join the crank. Let me see where the crank is at. The crank 7. Okay, so this is it. This is this crank here. So we're going to say, let me switch that off. So we're going to say assemble. What are we assembling now? We're assembling this crank with the connecting rod. So, and in this case, the connection is going to be a revolute connection. It's going to be a revolute connection, and then we have to select the snap place. This is where you will have a challenge. The snap here is very difficult to choose. In order for it to choose it, so it is convenient to switch off the first cylinder parts. So we switch off the first cylinder parts, and then after switching off the first cylinder parts, I think it is also good to switch off the crank. Aha. So it is inside this, it's inside that pin that we want it is the axis of that pin that we are interested in. So we're going to select it now. Once we select it, we are going to switch on back again the things we turned off. So if we're happy, we have chosen 2 things. We have selected the snap, we have selected the revolute, and we have said okay. So let us go and test that joint. We test the joint, we animate the joint. That animation didn't work, so let us animate it with the joint directly. Okay, it didn't work again. Animate joint. Animate joint relationships. Aha. So you can see when we animate the joint relationship, you can see that the crank is rotating around that. It doesn't matter when two things are, when one thing is rotating on the other, it doesn't matter which one is rotating on which one. So you can see that shows that we have got that right. So after getting that right, the next thing we want to do is between the cylinder and the piston. So between the cylinder and the piston, so we're going to choose assemble as built joint between the cylinder, oh no, not that one, not that one. Assemble as built joint between the cylinder 7 and the piston 7. And then it is a sliding joint. It's a sliding joint, and the joint is sliding in that place. So it is testing that and showing us that that joint has been done correctly. So the next one, maybe second to the last, is between the pin of the piston and the small end of the connecting rod. So when we are okay with that one, so we're going to choose the next assemble as built joint. We're going to choose to get to that, we have to turn off the cylinder again. And then we would also need to turn off the piston body, not the whole piston, just the piston body, leaving the pin intact. So if we come here now to pick the things to assemble, let's see. I've turned these ones off. I don't know why they're not going off. Let me do the turning off first before I do the assemble. So we are now in number 7. We are turning off the cylinder 7. The cylinder 7 goes off. The piston body goes off. Aha, yes. Now, we want to make sure that this and this can be connected in a revolute joint. So we say as built joint. As built joint, the parts are the connecting rod and the piston's pin. And then we want to select the snap. The snap is in this axis here. Oh, no. It's not a slider. It is a revolute joint. Aha. So that is the revolute joint. That is correct. So we can turn on the things we turned off before, which is the piston's body and the cylinder 7 is turned off before. So the last thing to do is to now rotate this to 240 degrees. So we are going to choose rotate, which is rotate here. And what body do we want to rotate? We want to rotate this crank number 7. The crank number 7, where is it? Crank 7. Yes, this is a crank 7. We want to do a rotation of the crank 7. So no, it's not bodies, it's components. The component we want to rotate is crank 7. We want to rotate it through what? Through what? We want to rotate through which axis? This is again where difficulty comes. We want to rotate it through the axis of this rotor, this outside rotor. That is what we want to, it is the axis of this rotor that we want to use for the rotation. So, and we are going to rotate it through 240 degrees. So we can begin here and start taking it to 240 degrees. And see, it is 115 here. We can actually type 240 degrees so that it will be accurate. 240. So it is 240 degrees. Now, there is a problem because it's not supposed to bring out this thing from inside that place. So there must be some connection that we didn't do properly. So let me undo that. That is Control Z. We are almost done. So let us see. We turn off the cylinder 7. We turn off cylinder 7 and we turn on the piston body internal 7. So let us do again. Assemble as built joint. This one and the pin. So the snap, select the snap. That's the snap. And then choose a revolute. And then say OK. Probably we didn't accept the OK the last time. So we can turn these ones on. You can see how funny these things can become. So let us now do the rotation again. The rotation, the crank rotation. The crank rotation, we select the components to move. It is the crank 7. And then the axis of rotation is this. And then we are turning it through 240 degrees. So we add 240 degrees there. 240. You can see now that it did not, the other constraints are on. The last thing we do, we are now going to join these two cranks together. We start making our crank. We're now getting a crankshaft. So we're going to assemble, and in assembly, we're going to do a split joint, and to be between the crank here and the original crank. The two of them are going to be given a rigid joining. So when we are okay with that, let us now test that last rigidity. So animate the joint. So you can see the first two cranks are now joined rigidly. So last thing now is that we are going to test the relationships. So you can see now the two cylinders are now working, and you can see that they are working at different angles. The time this one gets to the bottom top is different from when this one gets to the top. And that's what we're going to do for the rest. We're going to use the angles that we have determined. When we do that, let me just show you what we now get at the end of all of that. At the end of all of that, we get, let me just show you the result at the end. It is, I have the result here in my drawing called new assembly. Once I show you that, I think our class is done. The new assembly here, open. Okay, so if I take the joint here, this is where I've finished everything, and I do this, so you can see this is where you are going. This is what you are shooting at. We've done the first two. Just look at how we did the first two. You do the other ones, but check the original spreadsheet in your slide that will tell you how much rotation you put on each one. What I am saying is that I am going to give each student a completely different firing order. So your firing order is determining your crack angle, and you must do everything on your own. Your cylinder, your piston, everything must be yours. And I will check your drawing directly. If I copy anybody, I will warn you on time, because I want you to pass. I don't want to fail anybody. It is not my wish that anybody fails, but it is my wish that every unserious student fails. So just notice that you must do your work and you must be consistent. I think we have taken too much time already today. So I want to release you now. Wherever I would look at the notes and what we have not covered, I will see whichever one we can cover next lecture. Have a nice day. Goodbye. If you want to comment on the chat, I will still look at it before I go off this. I'm still going to look at the chat. Okay, okay, admin, please do a compilation of the names and addresses.
Okay, sir.
No, we will talk about that later. Fatima, we will discuss that later. We don't have time because I've already exceeded my time. So you will get your crank orders. Don't worry. I can send it to your email. Of course, it can be. But it will be your own. And you will not know the other people's crack, but just know that it will be different from every other person's own. So you must do your work. Admin, if there doesn't seem to be any other student like to chat. So I think I want to leave now. So bye-bye.